We got ketone, and then we have a reagent called alkylate, which is a bulky, strong base. And then if you look at the reaction conditions, negative 78 degrees. Why I have to give you the specific condition is, this ketone have two alpha protons, one here, one there. If that proton comes out, it's going to make a more substituted enolate, which will be more stable. If the proton substituted out from that position, it will make an enolate with a less substituted enolate, so less stable. But LDA is a bulky, strong base and low temperatures. It's not going to go after the most crowded side. It's going to go to the more open side because that's easy to access. So this proton is the one that get by an LDA. We call it enolate. It's called a kinetic enolate. Right? Kinetic enolate will be formed, and that will make an attack to this alkyl halide, allyl bromide there. And then that allyl groups are connected to these positions. Then question goes, if you want to connect the allyl groups go to this position, what do you need to do? Right? If you want to make these enolate forms, then you need to use a conventional base and then higher temperatures, like room temperatures or heat temperatures. If you're using a weak base like this from the dark side, it will pick up the proton from there because of that way you can create a more substituted enolate. So that will be more stable. So you've got to do it in the higher temperatures to form the more stable enolate to be formed. That more stable enolate will attack the same alkyl halide and you get that. So different condition makes a different product. There's a kinetic enolate, there's a thermodynamic enolate created by different conditions or different bases, different temperatures. So that is something that you got to pay attention to. And the question could come here, what if I use this weak base in the low temperatures? Then will I get a kinetic enolate or thermodynamic enolate? Or if you're using the weak base at low temperatures, this deprotonation is not going to happen. You don't get no reaction. So these things are not going to happen well. So that's why that question becomes a bogus. Low temperatures, if using a strong base, still the enolate can be formed. But if you use a weak base, enolates are not created. So it's not going to be like that. It's not just low temperatures that guarantee the enolate. It's a strong base, strong, bulky base at low temperature. That specific set of the conditions is what makes a kinetic enolate. All right, the next reaction I show you here is we got ketone, and then we are reacting the ketone with dimethylamine. Dimethylamine is a secondary amine. This nitrogen has two methyl groups. Two is a secondary amine. If you remember that dimethylamine with the ketone initially forms iminium ion, right? But iminium ion is not stable since it has alpha hydrogen there. So what happens is, these alpha hydrogens are taken away, then you get enamine forms. So this is a basic something that you should remember. Ketone or aldehyde reacting with a secondary amine, if an alpha hydrogen is available, it's going to make an enamine. If there's no alpha hydrogen, then it's going to stop with the iminium ion. But if alpha hydrogen there, then it's going to gain it. That is a nucleophilic carbon there. This benzyl bromide, what happened with this nitrogen lone pairs coming in, making carbon that double bonds, that electron, pi electrons that comes out, make an attack, and then that's how we make this bond. Once that happens, this iminium ion has to create, but it will be hydrolyzed by the water in the end, and you get the ketones. So this is just alkylation reactions of the other positions, but done by the enamine, not by the enolate, but the enamine. But enamine is a more strong nucleophile compared to enol. I mean, enolate is a better nucleophile than this, but it is a better nucleophile than enol. Enamine is actually something in between. So you actually, this is pretty nucleophilic carbon. The reaction can happen pretty well. You can do the same reactions using sodium methoxide. For instance, if you're using a sodium methoxide there, I mean, this molecule has only one alpha hydrogen. There's no hydrogen there, so you cannot make an enolate on this carbon. You can only make an enolate from that carbon. So that's the one that you create by reacting with the methoxide. Then you just using the same bromide, and you can get it done the same way. Why one wants to do the enamine instead of the enolate? That base, if you happen to spill on your skin, you'll get the first degree burn. That base, somehow if you happen to spill on your skin, you just wash it off, everything's fine. Much more safer. Our body don't have this. Instead, our body may using this. It may not be these particular forms of amine, but secondary amine we have in the body. We're using it to make amine and do the reactions. So that's how we make organic molecule or biology make molecule. So that's how nature works. All right, let's talk about how to make this from that. So which carbon of the starting molecule is the one that used to make that one? Is the first thing that we need to recognize, right? This is the ethyl groups. That is not this. I mean, somehow this methyl never turned to the ethyl by themselves. So you can easily see that this ethyl must be that ethyl. This carbon is that carbon. What it means is we need to connect 3 carbon unit propyl groups to this carbon. So what we need to use is, first of all, make an enolate, right? We're going to make an enolate. And then, in order to make that enolate, you need to worry about enolate at that position is different from enolate at the other position. This one is a kinetic enolate, right? It's a less substituted site. So you have to create not only the enolate, you've got to make a kinetic enolate. So how to make a kinetic enolate is something that we talked about. You've got to use a strong, bulky base at low temperatures. So LDA, negative 70 degrees, is the way to go. If you treat that, you're making this protozole, you make a kinetic enolate. Since we recognize this is the bond that we makes it to make these products, you need a propyl groups, like the propyl bromide, propyl chloride, then this will make an essential reactions, fix it up, you can basically make that. So we've got to recognize what we need to use in order to make that something that what region we're going to choose. If using conventional base, then what enolate is going to be created using this one is this hydrogen on the mole substitute carbon is going to be taken away. So you get the thermodynamic enolate. And that will react with this propyl bromide, right? Then you're going to get the propyl group substitute of that position. So this is what you will get. If you choose the wrong base, you will get a different product. Even though you pick an LDA, as I said, LDA is not guaranteeing that you get the kinetic enolate. You've got to do it in the low temperatures. So this must be set, not just one part. Just putting down LDA is not enough. LDA at the room temperatures, you get the thermodynamic enolate. So we're missing this part. If you're going to kinetic, these two has to be there together.